harder than it needs to be.
Okay, so recording has started. So the session has officially started. Let's wait few seconds. I want Amit to be back and or okay, let's start, and when he will be back, I mean, we can, before his presentation, we can try. Maybe he can go last. So, okay, welcome to the session. This is machine learning with and for software engineering. And our first speaker is Professor Tim Menzies. And as I said, we will have 5 papers, 5 minutes each. And then we will have open discussion for the rest of the time. So the team, the floor is yours. Team, are you? Team, I cannot see Team anymore. I think he got disconnected. Amir, do you want to try once more?
Try again, yes. Hopefully it works, otherwise I can give you my slides and
yeah, we are running out of time. Can you try once more? And otherwise,
yeah, sure. 1 second. Yeah, I guess.
Yeah, this is working now.
Yeah, perfect. Yeah.
Okay. While we are waiting for Tim, why don't Will you go? You are the next one in the list.
Sure. Let me start sharing screen. All right. Hopefully, I can't see y'all once I'm sharing screen, but hopefully y'all can see my screen.
Yeah, it is working. Good.
Excellent. I will jump right in then. So my name's Will, and I'll be sharing our work today on strategies for use and sharing among data scientists and software teams. So we've really seen data science proliferating, and it's become this highly iterative exploratory practice where the tool of choice here is a computational notebook. So I have one in the bottom right of the screen where I'm writing code and getting the results immediately below. However, computational notebooks have been shown to have some issues. They can be messy and non-reproducible. They might lead to bad coding practices because of unexpected execution orders. And their users tend to think less about the future use of their code. And all these issues compound to make finding, sharing, and reusing past analyses particularly difficult. And reuse is really the standard in software engineering. Modular reusable code has been a staple of effective software engineering for decades at this point. There's a variety of rich online repositories to actually help facilitate this sharing and reusing, whether you're in JavaScript, Python, or R, and a variety of other communities as well. Research has shown that proper use leads to fewer bugs and higher developer productivity. And there's a variety of principles like don't repeat yourself really baked into the ethos of software engineering. And so that leads us to our primary research question for this work of how does the exploratory practice of data science fit with the fundamental task of finding, reusing, and sharing past analysis work? So to actually answer this question, we did an interview study and a follow-up survey with data scientists at Microsoft. So this led us to 3 primary area of themes. So the first were some comments on data science workflows, about how are data scientists actually going about their work, what are the size of their teams. Next are 5 strategies that we identified from these interviews on strategies for actually finding, using, and sharing past work. And lastly were some influencers on sharing practices. So I'm mostly going to focus on this middle category, but I'd encourage you to see our paper or the 20-minute talk for more details about these other themes. So if I dive into these strategies, we've organized these from those that we think take the least effort to the most effort. So the first 2 are just sharing and reusing at the personal level. So the first one is personal analysis reuse, where I'm just copy and pasting past analysis code into my current analysis to actually reuse it. And this is probably pretty familiar to most of you all that are doing coding or just data science work in general. The next is a more formal version where I'm actually cleaning up my past analyses into a utility library. And then the latter 3, 4, and 5 here, actually team sharing. So the first team shared analysis code, strategy number 3, requires more cleaning of this code and sharing among the team. And then I'm actually going to go into a bit more detail about 4 and 5 here because I think that they're a bit more unique. So we think about team shared template notebooks. What these are cleaned, generalized notebooks for a task that have been shared to a central store. So these might be template notebooks with to-dos at the top. So if I have a notebook about training a machine learning model, say, okay, point this at your new data or change the learning rate. Or we might be actually using notebooks as functions or libraries. So here I have an example of having a notebook on the left, calling a notebook on the right like a function. This is an untraditional use of a computational notebook. So this is interesting because it's an example of data scientists actually adapting an experiment-based tool, the computational notebook, to really support and reuse. And this reuse can happen on the platform where work is done, in this case, the notebook. And this is meeting people where they work. As one of our participants said, they like using template notebooks because when the code requires customization when applied to different scenarios. Of course, the drawback of this is that it can be hard to maintain updates across so many notebook forks and tweaks. This is distinct from more of a traditional library for sharing code that has the benefits like modularity, updating, and versioning. However, some people still prefer easy customization and debugging afforded by template notebooks. That's one of our key takeaways here, is that the nature of data science work doesn't always lend itself to traditional libraries for analysis code. And so I'm going to talk a little bit about influences, but not go through all the ones that we identified. But I think a key one here is that team culture must incentivize the time investment necessary to actually clean up and share this code rather than just copy and pasting your own code. As one of our participants said, sharing code in data science is often not rewarded at the level needed to offset the investment necessary to do it well. So that brings me to some of the implications that we thought about for this work. So the first is that the outcome of data science is not actually the analysis code. So people aren't actually sharing the code that they write, rather they're sharing slide decks with the result of that analysis, reports that are written about these analyses, or the actually models themselves. And so for tools and future tool use, we think that future tools might support a tighter coupling between presentation environments, like the one shown on the left, and coding environments, like the one shown on the right, to support this tighter coupling and a faster analysis loop. The next key takeaway here is that customization is really essential for use. And so data science code can rarely be reused out of the box. It often needs to be tweaked. So if I have a template notebook on my left, I need to adapt it in 3 different ways for 3 different analyses. This is partly why template notebooks are so powerful. Lastly, a lack of tool interoperability really limits reuse. So if I have analyses in Python, SQL, and R, it can be hard to actually reuse these in different environments. So this has been strategies for use and sharing among data scientists and software teams. Thank you so much. I encourage you to either scan the QR code or follow that link to see our full paper or the 20-minute talk. And I'd be happy to take any questions. It sounds like later in the session. Thank you so much.
Thanks, William. You are right on time. Great.
Thank you.
So, okay, let's go to Yao's talk.
Okay, I will share my screen. Okay.
Mm-hmm.
Okay, could you see my screen now?
Yes, yeah.
Okay, then I will start.
Mm-hmm.
Hello everyone, this is Yao Wan from the Huazhong University of Science and Technology. Here I will present our work, which was titled, What do they capture? A structural analysis of pre-trained language models for source code. Currently in the domain of software engineering, various works have been proposed to apply machine learning techniques into automated the software engineering tasks. In this kind of task, code representation learning, which aims to encode the code semantics into distributed vectors, is the fundamental of code intelligence. Recently, pre-trained language models of source code, which are based on self-supervised learning, have attracted much attention, such as the BERT and CodeGPT and GraphCodeBERT, and so on. As we know, these pre-trained language models of source code are very large and complex, and they are can be seen as a black box. And we think that it is still not clear why this model work and what future combinations they can capture. And in our work, we aim to open the black box of the pre-trained language models. And specifically, we aim to answer the following research questions. Can the existing pre-trained language models learn the syntactic structure of source code written in programming language? In our work, we aim to investigate 3 research questions. The first research question is, does attention align with the structure of code? You know, in the pre-trained language model, the core module is the transformer, which is based on the self-attention mechanism. So in this research question, we aim to analyze the attention in each layer of the transformer. In this question, we define we define an equation to measure the portion of the attention. This, for example, this is the equation we have defined in this question. We can say the alpha ij denotes the attention from the S code token to the JS token, and we think that if the code token in the AST shell are close, their attention should be expected to be high. And in this equation, the F, Wi, and J returns 1 if Wi and Wj are in the syntax relation. So use this equation can measure the attention, the relationship between the attention and the structure of code. And we conduct experiment to verify this question. The experiments reveal that the attention can align strongly with the motif structure of AST, especially in the deeper layers. And in our second research question, we aim to investigate, can pre-trained model embed the syntax structure in its contextual order embedding? We propose a word probing approach to probe the order embeddings in each layer of the transformer. The key insight of our approach is that the tree structure is embedded if in the transformed space, the distance between the 2 words vectors should correspond to the path length between the words in syntax tree. For example, in this AST, the length between the define and the function define is 1, and the length between the for and the token in is 2. So our assumption is that if we can map this the original order embedding into a transformed feature space, their distance should also be equals to 2. So that we can, so this mapping function, we can transfer the original into the transfer space, and we aim to learn the mapping function B, show fast learning approach. So this word probing approach, our experiments reveal that
Now, we have 1 more minute.
Yeah. Okay. I will end this one. The syntax structure of code has been well preserved in different hidden layers of a pre-trained language model. And we also conduct a third research question. The third our question is, are pre-trained able to induce the syntax structure of code? In this question, we propose to induce the syntax structure of source code from the order embedding. Our key insight is that if the distance between 2 words are close, they are expected to be close in the syntax tree. For example, the vector of token OPT and the vector of meta are similar. And our assumption is that their distance between the AST should also be close. So based on this insight, we propose a greedy top-down inference algorithm based on the partitioning of the input. Using this algorithm, we can induce a syntax tree based from the order embedding. Okay, this is a case study to show the effectiveness of our induced syntax tree. For example, in our induced tree, we can observe that multiple structure of code have been learned. Okay, this can show that the pre-trained model can capture some multiple structures of source code. Okay, that's all. Thank you. Okay, then I will end sharing my screen.
Baishan.
Hi, Professor Rui. Maybe you have muted your voice.
Tim, sorry, I didn't notice that. Tim, do you want to go now?
Sure. Share screen. Trying to share screen window. Okay, then. So I want to talk about oversampling and deep learning with my student Rahul Yeti. We've been worried about how people are using some deep learning and software engineering kind of uncritically. If you look at recent publications in defect prediction and deep learning, most of them do not compare what they do with a non-deep learning source. Most of them don't do hyperparameter optimization, and most of them don't address oversampling, thinking that the deep learner itself can handle all the issues associated with feature engineering. This is unwise. If you look at Java systems and you look at the percentage of defects in the training and test data, you notice that there's a lot of mismatches. It's not like even. If you look at the results from this data, down here, the blue means you're getting F1s of like 80% or above. When the ratio is about the same, everyone's just fine. But as soon as you get into the point where there's there's a lot of examples in the test data or a lot of examples in the training data, you start seeing very poor performance. What you need is methods to better adjust the hyperspace boundary. And the message of this talk is that our deep learners aren't doing that as well as we thought they should, and we can repair that. We're recommending local adjustments to the hyperspace boundary. Hyperspace boundary is what divides examples. This hyperspace boundary here is very good for separating the orange examples, but terrible at separating the blue examples. There's lots of misclassified blue examples as orange here. We know things like in support vector machines can do their parameters to adjust these hyperspace boundaries, but we notice that those policies are global across the whole data. We recommend we stop adjusting the boundary global to the whole data, but start adjusting the boundary with local information. For example, when we do the weighted loss function, we separate out the minority class and the majority class, and we put in this WI on n term just here. N's the fraction of the data that's a minority class. Doesn't matter much what that WI is as long as it's non-negative. This is one simple way to adjust. Another more powerful way to adjust the barrier locally is you go to the minority classes, and at various radiuses out from that minority class, with decreasing probability, you put in artificial examples. Now, what this means is that you have the sheet of all the data, and here's an example, and here's the hyperspace boundary. By putting in more examples here, you're building a hill, pushing away the hyperspace boundary at that point. And that's what we call fuzzy oversampling. Down here, we see our preferred methods, and here we see the results, median and IQR, which is 50th and 75th minus 25th percentile, F1. For this data, very nice numbers, 80%. But if you go to a standard advice down here, this is an ablation study where we take our recommended method and we throw things away. And we're recommending this stuff because every time we do anything less than this stuff, the performance goes down, 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 down. These first four examples are summarized as just use the off-the-shelf details. Just use what everyone else recommends to do. And we're getting very bad performance for this data because of this imbalance problem. Once we start doing fuzzy oversampling and tuning, and here we're tuning the differential evolution, you can see the first big performance bump, and now we're getting like 50% IQR for F1s, very large. And this second big bump here, 51 to 81, occurs. You see the 2 ticks here? We found that if we do the fuzzy oversampling for the minority class, and then also for the majority class, we get this very large performance bump here. So the paper is here on GHOST, the fuzzy sample, contact us. This is actually an example of a more general process. It turns out that we've got many more operators for making local adjustments to the hyperspace boundary, and we're working on those. We're happy to send you a paper that we're ready in the next week or two. So that's my talk. Please stop using hyper deep learning off the shelf. Please stop assuming that it will do the feature engineering for you automatically. That may not be true. Please recall that the field's called data mining, not algorithm mining. Stop applying algorithms blindly. Look at the data, look at what you're trying to do, and reflect upon how you can better manipulate the hyperspace boundary in the local region to achieve much better results for complicated data sets. Thank you very much.
Thanks, Tim. And we will discuss about all the papers after all the talks are over. So we have 2 more talks. So the next one is Amir.
Yeah, I'm going to share my screen.
Yeah.
All right. Hi, everyone. My name is Amir Mir. I'm a PhD student at TU Delft. And today I'm going to present our technical paper, Type4Py. As we know, the Python programming language is easy to use and it allows rapid prototyping. On the other hand, and due to the lack of static type annotations or static types, Python developers often encounter type errors like this example. And of course, Python has a support for optional type annotations in 2014. However, adding types is a daunting task, and motivated by this, researchers have recently proposed machine learning-based type prediction models, and also we also have some tools, static type inference tools for this task. In this space, ML-based type prediction, we have identified the challenge and a problem. The challenge is to suggest the correct type in the top 1. The research has shown that developers tend to use the first suggestion by a tool. On the other hand, machine learning models, usually give top 10 suggestion or top 5 suggestion in lists of predictions. And of course, it's very challenging to suggest the correct type in the top 1 in the first occasion. And also the problem is that developer provided type annotations may not always be correct, and therefore we need to type check our data set at least for evaluation to make sure that we have a correct ground truth. In this paper, we propose Type4Py. It is based on deep similarity learning and hierarchical neural networks. And we also provide a type check data set. And last but not least, we also provide a Visual Studio Code extension that provides an ML-based type of completion for Python. Now I would like to talk about our proposed approach. This is the overview for proposed approach Type4Py. First, we extract ASTs from Python files, and by analyzing abstract syntax trees or ASTs, we gather features like identifiers, code tokens, and visible types, and we convert those features to token embeddings or vector representation for the model to learn. And at the prediction phase, we have type clusters, and we perform k-nearest neighbor search to suggest types. I have one code snippet here to explain the type hints or features that we extract for the task of type inference. Visible type hints are basically extracted from import statements and its transitive dependencies from Python files. And identifiers are basically the name of the function, parameters, and also variable names. And also we consider code context as a hint, which is basically the usage of parameters and variables inside the function body, as shown in this code snippet. This is our neural model, and we have two recurrent neural networks with LSTM cells, and we finally have one linear layer that produces type embeddings that is used to create the type cluster. We have extended our many types for data set for this work. We perform coded application, which is an essential step. And we use the Poirot tool to augment our data set with more variable type annotations. And we also use MyPy to type check all the source code files in the data set to make sure that we have valid ground truth for both training and evaluation. Now I would like to talk about the evaluation of Type4Py. We have overall 3 research questions. And due to the time constraint, I only present the first research question. The first research question is basically type prediction, but overall type prediction performance of Type4Py compared to other baselines like Typewriter and Typewriter. Considering the top one criteria, an exact match, Type4Py achieves around 76%, which is significantly better than the state-of-the-art approaches in this space, Typewriter and Typewriter. And also considering the MRR or mean reciprocal rank, again, Type4Py outperforms both state-of-the-art approaches. And I would like to also talk about our deployment in practice. We have a Visual Studio Code extension that works on developer machines. We also have production models on our Kubernetes clusters. And we also provide a local model for developers for privacy reasons. As I said, we have Visual Studio Code extension that, as of now, it has more than 1,100 installation. And this is one example, ML-based type of the completion in the VS Code environment. It gives developers a list of suggestions for type predictions. To conclude the work and consider the future work, pointer networks might be a promising direction to try to suggest new types. And we would like to also study how to improve Type4Py from its usage in VS Code and using our telemetry data that we have so far. And last but not least, complementing Type4Py with static type inference might be also a promising direction to try. And thank you so much for your attention and joining our session. That was my talk. And also you can check out our GitHub or also dataset if you want. That's free and open. And also you can check out our preprints on arXiv.
Thanks, Amir. We will talk more about your paper soon. And then last but not least, we have Rangit to present his paper.
Can you see my screen?
Yes.
Thank you. Hi, everyone. My name is Rangit Pan. I'm a fourth-year PhD candidate at Iowa State University. Today, I'm presenting our work with my advisor, Rajesh Rajan. I'm going to tell you about an approach to decompose convolution neural network into modules to enable reusability and replaceability. We envision that decomposing model into modules can help to solve real-world problems. For instance, in the past, Google Photo app tagged a black woman as a gorilla. Not only that, recently Facebook, currently known as Meta, also had a similar instance where a black man has been labeled as primates on a video. While we do not have information how Meta resolved that issue, we found that to resolve the similar issue, Google has decided to remove the output class gorilla by suppressing the output level. In fact, they have suppressed the output for chimpanzee, monkey, chimp, etc. from the model that recognize a wide range of images like car, human face, etc. Though the problem can be temporarily solved by suppressing the output level, to fix the model, one needs to retrain the model. Suppose we decompose the faulty CNN into modules, one for each output class. Also, suppose we have another working model trained with the same or a subset of data set with gorilla and person output levels. The latter model does not exhibit the behavior present in the faulty one. Then we can decompose the model into modules and replace the faulty Gorilla module with the working Gorilla module that does not exhibit the incorrect behavior. Other solution can be creation to include a creation of small model and use it as modules. Or we can remove the Gorilla module from the collection, which is similar to what Google did to resolve the problem. To introduce the notion of the decomposition, in our previous work published in eSpsychology 20, we proposed an approach to decompose the dense-based deep network into reusable and replaceable modules. However, that work focused on the dense-based network and did not explore more complex set of deep learning techniques, such as convolutional neural networks. That work relies on dense architectural model where nodes and edges have one-to-one relationship. In contrast, CNN weights are shared among all the inputs and the output nodes. The prior work performed backtracking mechanism to decompose the module, which is only applicable to the dense-based layers. Our approach starts with a trained model. For instance, in this case, a model that recognizes images labeled as A to D. First, our approach identifies the section of the CNN that is responsible for a single output class. Since we remove the nodes for all the non-constant output class, the identified section acts as a single class classifier. To add the notion of the negative output classes, we add a limited section of the input for unconstant output classes. Finally, we channel the constants to create a module. In this context, we use the constant and unconstant terminology that represents the input belonging to output class for which module has been created. For example, for module A, output class AA is the constant output class, and other classes such as B, C, D are the unconstant classes. We answer 3 research questions. Does decomposition involve cost? How modules can be reused or replaced to build a new problem compared to training model from scratch? And does reusing and replacing modules emit less CO2? Overall, we found that there is a cost of decomposition, but it is trivial. Also, we showed the possibility of reusing and replacing modules. Also, we found that for all the cases, composed models using modules emits less CO2 compared to the model trained from the scratch. To that end, we propose an approach to decompose convolutional neural network for image-based classification problem into modules, one for each output class. We show how real-world issues such as issues that Google and Meta faced earlier with incorrect classification can be addressed by decomposing model into modules. We discuss the methodology, a 3-step process taking a monolithic model as input. The output is a series of modules that is a binary classifier. We answer 3 research questions related to cost of decomposition, possibility of reusing and replacing the modules, and the consumption of CO2e in reusing these modules compared to the model trained from scratch. We made the preprint available where you can find more detailed description. Also, that longer presentation is available at Confra Researcher. Thank you.
Thanks, Rangit. Okay, so now we are ready to discuss. Any question from the audience? Can you please raise hands? Okay, so, okay, let me start, and please, guys, jump in, and then let's have a very, vibrant conversation. So, let me ask the speakers first, and then we can take the audience. Rangit, do you have any questions for the others?
Yes, actually I do. So I have one question for Will. I was reading your paper, and you mentioned the reuse of the notebook. So I was wondering, when developer reuse the notebook, do they reuse as code they just copy and paste, or they need to change? Maybe, for example, the library version changed. The previous functions are not working because the signature or the naming convention has been changed. How often do you see those scenarios, and what kind of efforts that needs to be done to reuse these notebooks?
Answer your question. So basically, when people are reusing notebooks, like what do they need to change, or why are they having to change things? Is that the question?
Yes, that would
Yeah.
be more interesting.
Yeah, so I think there's a variety of regions. That's a great question. Thank you. So I think one common one is that, so if you think about, like, if I have a script for like pulling data from some database and then cleaning it and then feeding it into maybe another like model pipeline, maybe my data has changed a little bit. So I used to not have any nulls and now I have nulls in my data. And so that pipeline might break. So I need to add in like a new part of my script to drop nulls. Or maybe the column names have changed a little bit. I think that's less common with what we were seeing in some of the like production databases at Microsoft, is that the actual schema wasn't changing that much, but like each time they might have to change the cleaning script a little bit, or the actual analysis task might be different. So last time you have 100 columns in your data, I wanted these 4, and then now it's the same data set, but a slightly different task. So I only want to reuse part of that analysis. So I think it kind of points to the fact that like a lot of data analyses are slightly unique, and like sometimes they're like very similar, sometimes it's like a little bit unique. So it needs to answer your question. Thank you.
Yes, and that's, thank you.
Okay, Will, actually, I have a question on very similar topic. So you said that some developers don't feel rewarded. So how do they feel rewarded? Like what will feel them rewarded?
Yeah, that's a great question. So basically, like, how do you incentivize people to want to invest this time? I think it's a tricky question. The people that we talked to, I think it was more. So I think that like something I mentioned at the end of my talk is that like a lot of what we found in data science is that if I'm like giving a presentation about data analysis I've done, people will rarely want to see the code that they're more concerned on like, was this valid? What statistical techniques was I using? Was my data valid? And so for me to actually go and share that code with my team or with other people requires this time investment. And so if some people's like it's like felt very top down, like if someone is saying, okay, we really want our people on our team to invest the time to share their analysis code. Like don't just share the slides, but share the code with it. And if they're told from like top down that, hey, we want you to do this, and they feel rewarded, but if I'm having to do it on my own time, then that's, of course, like time is valuable, right? Like there's a million other things I could be doing. And so I think it kind of more points to the tension of that, like, if it's made explicit that they want this to be done, then people will feel rewarded for it. And I think particularly if other people are using that code, like if I share my code with you and no one on the team ever uses it, then it kind of feels like a waste of time. But I think there's some nuance there for sure. Thanks for the question.
Great. Okay, so let me see. Will, do you have any other question to other speakers?
I have one question.
Yeah, I had a question.
Oh, sure. I mean, go ahead.
Please go ahead.
Yeah, I had a question for Tim, if I could, a pretty short one. So something you mentioned, Tim, is that you found that, my understanding was that oversampling the majority class also led to better performance when you guys were talking about these different training methods. And that was a little bit unintuitive to me. I was curious if you could like try to help me understand why that was effective.
Well,
like
I think
to me, oversampling minority makes sense, but why that was effective as well.
Just going back in time, have you ever applied SMOTE, oversampling? You take data sets and sort them by their oversample amount, and then applied SMOTE across them. And when I did that, I expected that the more oversampling, the better SMOTE would be. Right? And I've got a NIXI paper 2 years ago where that doesn't happen. SMOTE improves the performance, but not more for the things that are undersampled. And so I've started to think that SMOTE is actually a signal amplification method rather than a sampling method. And so when you start thinking that what you're after is signal over amplification, it makes complete sense that if you can find the boundary and find a wriggle, a dimension where you can push it away from particular instances, you're removing the noise points where if something's got noise, it jumps one class to another. So I think sorry, that's too long an answer. The short answer is I think we need to rethink what we mean by oversampling and why we think it's useful. Would be my challenge back to the research community.
Thank you.
And I have a question for Ranjit.
Hi, Professor Manjit.
Hey, how you doing, man? So the question's in two parts. The first is what you've done is impossible, and you need to revise everything I know about deep learning. And the second thing is your approach is possible, and I want to see some benefits from it. So assuming that it's impossible, my mental model of a deep learner is everything's massive, great, fuzzy, massive connection. And snipping out any bit is like reaching into your brain and pulling out your knowledge of grandmother, which is all over the place. So I think you need to help me understand what you mean by dividing a network. And assuming you can do that well, I want to know whether the divided network has certain interesting properties. Does it train as well? Does it train faster? And that last question is really important to me. So is your stuff impossible because you can't divide a deep learner? And given that you can divide it, are the divisions better for accuracy or training speed?
Okay, to answer your question, first of all, we decompose the trained model. Our input itself is the trained model. And the output is the modules that's decomposed from. So for example, let's take an example that we have given in our previous paper also. We have a model that trains for MNIST dataset for 0 to 9. And tomorrow we want a model that's for binary classifiers, 0 and 1. The way developer will going to do, they will going to partition the data set, take the example for 0 and 1, and going to train a model. What we are proposing is that we already have a trained model. Why don't we break it into parts? One part that is responsible for only 0, and part responsible for 1, and so on. If we can break it into parts and reuse those parts, we can solve the same problem that required the data partition and training and so on, which can be entirely avoided. That was our motivation to do that. And in fact, when we say modules does not need to be trained. Modules are coming from the trained model, and since they are.
But if you want to update your divisions, do you go back from the start and rebuild the whole thing, or can you incrementally modify and update and maintain accuracy on the divisions?
Yeah, so that's a really good question. At this point, we decompose from already a monolithic trained model. If we need to modify that, in fact, you are exactly correct. We have to go back and modify it from.
Oh darn! Okay.
However, that is definitely a really nice work to do for the next or the future work, where we can update the modules. I mean, in fact, if we go back to the software decomposition, and we previously have a monolithic code, the first we decompose the code. So
I've got some follow-up stuff, but let's cycle to someone else and see if anyone has anything.
So what I was saying, that if we can decompose the monolithic code into parts and reuse those parts, that's one part where decomposition helps to increase the reusability, replaceability. However, we can definitely, one of the other benefits of decomposition is independent development and independent testing, where we can make those modules better or test. That is some of the direction we are currently working on. Is very interesting direction we think in future.
Thanks, Rangit. Yeah, I think Amir had some question,
Yes,
and then
one
we'll go to
question.
Yao. Yeah, go ahead, Amir.
So yeah, regarding the third research question, this is for Rangit. And how do you measure the CO2 emission of?
Okay, so the way we measure the idea of the CO2 came from, there's a paper in 2019 from Strubel et al. They said the training language model is very resource consumptive, especially CO2. Based on their insight is that training a language model takes 6 times more CO2 than a car running by fossil fuel over a year.
Sorry, how much?
6 times it takes than a car running on fossil
Times.
fuel over.
More than
Not only
a
that,
regular car on the street.
Yes. So not only that, even they are saying is that the amount of CO2 consumed by a flight journey from New York to San Francisco, it takes around, if I remember correctly, 3,000 times or something like that. I mean, if you go and forth 3,000 times from San Francisco, New York, you will train a language model. That's the so the answering your question is that there are ways to compute. In fact, they give a formula to how you can transform your computational resources, power consumption of RAM and other thing into a corresponding CO2. We exactly use that formula, and while training the model or decomposing, we take how much resource our systems are using and convert it into the CO2. Does that answer your question, Amit?
Yes, thank you.
Thank you.
Thanks. Yao, do you have any
Hi.
question?
I have a question for Amel, and for the task of type inference. Actually, I'm very interested in this task, and my concern is that have you as I know you may use the recurrent neural network to represent the source code, right?
Yes, we use two RNNs.
So have you considered to represent the structure of source code, such as the ASP or control flow graph, or some using the structured neural networks such as graph neural networks?
That's a good question.
That have been used widely used in cell state-of-art baseline, such as the TPLOS.
Yeah, like TypeLess. As you said, TypeLess uses graph neural networks.
Yeah.
And they consider control
So
flow.
consider to use
the code. But I mean, empirically, I mean, we showed that Type4Pi outperforms TypeLess, which is a GNN model. I mean, that's this empirical results, obviously.
Okay. So under you have also mentioned in your paper you mentioned that recently there is a pre-trained model and termed TypeBert, right? So do you consider to use the pre-trained model to represent the source code?
This is a good question. Yeah, that can also be, let's say, future direction. We can try to train a big, let's say, big pre-trained model for Python source code. I mean, TypeBit was trained for TypeScript, but yeah, that could be.
So
I have not tried it yet, but
yeah. So in my view, your contribution of this paper is not on the how to represent the source code, right?
The contribution of this paper is basically threefold. We have a type check data set that is not used in the previous work, like TypeLess and TypeWriter. We also present a new model Type4Pi. We also have Visual Studio extension that Python developers can use to gradually add type annotations to the code base, thanks to Type4Pi.
Okay. Thank you.
Did I answer your question?
Yeah, thank you. Thank you for answer.
No worries.
Someone's phone or something is ringing. Can you mute yourself?
It's not me, but I can mute myself.
Okay, so any question from the audience?
Yes, I have a question for again. Sorry, back to Randy. Yeah, sorry to talk to you so much. So my current best hint for speeding up the training and of hyperparameter optimization of neural nets are adapter layers. So you're taking a neural net, and my imagine is you're doing vertical slices to pull things apart. And the lesson of the adapter technology is that if you slip in really, really simple networks between the layers, those adapter networks are a candidate for tuning. Okay, so does that help you? Like you're dividing vertically. Have you considered horizontal slices.
Sure.
And feel free to say no, because it's not what you've been doing so far,
Yes, so far the answer is no. The reason for doing that, our end product, we wanted to enable reusability and replaceability. And when say reusability and replaceability based on the output classes, our design or decomposition criteria, so to say, what output classes. So based on that, since we want to decompose a module for one output class, we divided by vertically, as you say. However, if you think like the layer structure, they are already in some way decomposed in a sequential manner. One layer takes, they are in a modular fashion architecture, they are already there. So
not quite. The functionality, like let's say you want to divide by 0 or something. I'm imagining that functionality might appear as a column that comes up through multiple.
Yes, that's why we divide it into vertically, because that functionality is present. But if you want to decompose based on some criteria that needs the decomposition to be done as the horizontal, such as layer, that would be definitely another way to decompose. For example, layer architecture. Layer architecture where you have each layer that is decomposed into a vertical. Each layer does some function. It's also a module you can think in a way, and that is sequentially divided. So given that at this point, since our decomposition criteria was output classes, we decomposed via vertical. However, if there are criteria other than this, definitely we can decompose into different ways. In fact, going back to Parna's 1972 paper is that there is not a single way we can decompose. There are different decomposition approach, and it is based on the need.
I also wonder actually if you use non-CNN based architecture like transformer, and transformer by design is taking attention from many contexts. In contrast, CNN is more more localized, right? It is getting information in a more local context. So this concept of decomposition might be very different for transformer kind of architecture versus CNN kind of architecture, and which might be interesting to see.
Yes, and we hope it's more different than we can work on that. We have worked on dense and found it is different, and we found it made a work on CNN and it got into a paper too. If it's significantly different, then we can definitely, that would be our next work for sure.
Sure, yeah. So Yao, I actually have a question for you, like where you are looking at different pre-training model and the structure contribution. I saw in this table, the figure you presented, you saw both encoder and encoder-decoder kind of model, like BART style, BERT and BART. Do you find any difference there, or they are basically the kind of giving similar information?
You mean the some findings in the encode-decode network?
Yeah, so are there any difference between encoder-only network and encoder-decoder networks?
Okay, actually, in my opinion, I think in the encode-decode network can be seen a general framework in many NLP or software engineering tasks, and in our scenario, we only consider the pre-trained language model. I think the pre-trained language model can be seen with only a encode network. But actually, there is some pre-trained language model both for the encode-decode network. For example, the PL-BART, which is a pre-trained language model, which is for the encode-decode network, which can be used for some text generation tasks. But in our paper, we only consider some pre-trained language model which only consider the encoder network, and we didn't comparing the encoder network and decoder network in our work. But I think maybe it is interesting topic for our future work.
Okay,
Yeah.
that's good to know. Yeah, you have a few. I think that was like how big the models are, and there you showed some of the BART, like PL-BART Code T5 kind of models. So I was interested to know. But
Yeah.
okay, yeah. Okay. We still have 5 minutes. Any other question?
So I have one for you.
Sure.
Okay. Sure.
You discussed about how this language model, works on code related. How do you think your insight or the implication can be helpful to build language model for more complex tasks like code suggestion or merge conflict resolution? Can you please give us some insight?
Okay, I think actually there have you may know there have been many and pre-trained language model in the domain of natural language processing. I think in the program language areas, such as source code, I think the biggest difference between the program and the natural language is that the program is relatively more highly structured, right? And it has many logic flow in a program. So I think one challenge to applying the pre-trained language model in the source code is that how can we incorporate the structure information of source code into a pre-training process? For example, how can we incorporate precisely incorporate the data flow or control flow information in the pre-training process?
So
Actually,
I actually GraphCodeBot did that,
yeah,
right?
I
Do you
think
think it enough?
I think GraphBot is an attempt to incorporate the data flow information to the pre-training process. I think this is only a initial start. I think maybe we have more we need more effort to incorporate more price information, such as for example for the task of type inference, Emma has mentioned. So for the task of type inference, maybe I think maybe some statistical information such as the data flow or how the variable flows along the code is very important for the task of type inference. So how to incorporate the structure information into pre-training, I think is very important. And from our empirical study, actually the pre-trained language model, even though we don't explicitly incorporate the structure into the pre-training, actually the pre-trained language model, which are based on the self-attention mechanism, can capture some structure information. They have already captured some structure information. I think this is also a very interesting finding in our work. Yeah, overall, I think how to represent the structure of source code is very, very important for current machine learning for software engineering tasks.
So I feel, I mean, you mentioned, and I also feel the same, that because transformer is essentially a fully connected graph, and you are learning, if when you are using transformer, you actually are learning the edges, like the weight of the edges in form of attention, right? And then finding the graph structure. I think a very interesting direction to me is like on top of the basic code structure, transformer based model already have the potential to learn it. But on top of that, what kind of structured information can be fed to the model to make it even better?
Yes, but how to feed the structure into the transformer neural network, I think is also a challenge.
No, actually, lot of like Code-T5 did that in part thing. Like I think lot of new models, SPT code that was published in last year, ICSI from UTW.